Thank you for the invitation. I'm really happy to be here. Thank you for the organizing for making this great event. So I'm going to talk about, variational inference, especially thinking about applications. So this is a very big topic, and in half an hour I won't be able to cover all of the details, but I want to give everyone some potentially useful information. So even if you haven't seen this topic, like knowing what it is, and if you have used it, so maybe some tips and tricks that I've learned through some real applications. So the outline of the talk is first motivate some examples to like, why do we care about this? Then I'm going to talk about variational inference in a nutshell, meaning that I want to just go very fast on kind of the math, so to say, and then focus on kind of a concrete example so that we can make all of these concepts more tangible. So I'm going to start with a toy example just to get a flavor of it. And then I'm going to do a bit of a more complex example, but still relatively simple, which is a Bayesian neural network model. And at the very end, some tips and tricks and learnings, and of course, some references. So you can look into the notebook where you can reproduce all of the results, and I'll share the slides on the Discord afterwards. So I think there are many applications, but two of them on which I heavily use variational inference and Bayesian modeling has been in the context of demand forecasting and cohort model. So demand forecasting, I was faced with the problem of doing forecasting in retail at item level, so I don't know, oranges, apples, and then kind of it was very important for this kind of model to take advantage of the hierarchies of the data structure, and also something that we wanted to do is to have some control on interpretability, and also we wanted to do like kind of counterfactual analysis, which means we have promotions as a feature, and then we wanted to ask ourselves what would have been the sales if the promotion had been dropped or increased by X%. And this is where all of this kind of Bayesian framework comes really handy, for example, with the do operator, which was presented in previous talks. And one of these requirements is that this has to scale quite a lot. And we didn't care much about really specific kind of uncertainty around the latent parameters. So variational inference came up like a very handy tool, and we were able to train these models, let's say around 50,000 time series in a hierarchical state space models on GPU in like 7 minutes. So it does scale pretty well. Of course, there are some trade-offs. I'm going to talk about that later. And cohort modeling, it's another type of model that I work quite a lot on, which you want to couple retention with, let's say, a revenue component. And you do this at cohort level, and you can do this for a market, but maybe you have 25 markets. So if you want to just scale this and put this into production, then this came as a very good alternative. So there are many cases, but these are two which I really have used, and I'll be happy to discuss them afterward. So what's variational inference? Again, I don't want to get involved into the math, but the gist is that when we want to do Bayesian modeling, we want to start from, let's say, our prior about the parameters. We have the data, and we want to understand what's the distribution of the parameter given the data, which is the kind of left-hand side of the equation. And yeah, so far so good, but this in general is very hard to actually compute. So there are many techniques of doing this, and typically you use like MCMC or like Hamilton and Monte Carlo to get really kind of fine estimates. But so variational inference, what it does in a nutshell is try to frame this sampling problem and convert it into an optimization problem. Of course, there will be some trade-off, but then we can use all of the kind of machinery from gradient-based optimization. So for example, all of the learnings from deep learning to actually make this work. So instead of doing MCMC, we're going to find this posterior distribution within a family of kind of distributions that you would predefine. So that's the catch, right? When you run MCMC, pretty general. You can have bimodal distributions. In stochastical or like in variational inference, you actually need to impose certain parameterization over your posterior, which might fit your model, but sometimes it might not. And it's important to distinguish those cases. So again, this is kind of what we want to do, optimization. So when I was preparing this talk, I thought about, okay, of course, I want to start looking into PyMC. There have been a lot of really good developments in PyMC regarding not just variational inference, but other methods like Pathfinder and so on. But then Chris Fonesbeck came up with this amazing talk at PyData Virginia, which he I mean, he just did a fantastic talk, and I was like, it was an hour and a half tutorial. It's just great. So if you're watching this, click this first and then continue, because I think it's very worth looking to this talk. It's really, really the best introduction. So I had to pivot, right? So I was like, okay, what could be useful for the community instead of doing this talk again? Or of course, I mean, Chris is always going to do a better job. So I moved into another framework that I use quite a lot, which is the JAX ecosystem. And I saw this as an opportunity to also just showcase how kind of these tools can actually be integrated within a wider ecosystem. So most of the things that we could do here, we could also do in PyMC, but this is just to complement the material that is out there. And I think for the JAX ecosystem, there's not much kind of literature on how to start with this concept. So instead of PyMC, we're going to look into NumPyro, which is kind of built on top of JAX, which is a very popular numeric library. And we're going to use Flux to do some neural network because they're cool. And we're going to use Optax to do optimization. All right, so this is the only kind of heavy math slide, but I want to go relatively quick. So what's variational inference? Let's say, how do you turn this into optimization problem? So first, you start with the data. Typically, you have your X as features and Y's as outcome. Then you have you have your Bayesian model, you specify that, or your linear regression, and you have some parameters theta that you want to learn. And then you want to understand or compute the posterior distribution, which typically it's very hard to do. So what do? You say, I don't know what the posterior is, but I'm going to parameterize this into something that I think it's reasonable. So let us assume like, okay, maybe I can approximate all of this with a normal distribution. And this normal distribution will have parameters like the mean and the standard deviation that you would like to learn. And these are these phi parameters, which are the variational parameters. So if we learn phi, then kind of we're done, because we can actually compute the posterior distribution approximation from the parameterization. So how do we actually do this? Well, and this is kind of the magic, and it does the job quite well. There's the objective function, which is called the ELBO, and what it does is kind of captures the distance, or like in some degree the distance between the posterior distribution and the variational approximation. And it turns out that if you minimize this ELBO curve, which come from this formula, then it's equivalent to minimizing something that is called the KL divergence between our posterior and our variational approximation. And it's actually relatively easy to see if you go to this reference that I've seen below, that this is relatively reasonable. But there's something weird about it, because like, how can you approximate something that you don't know, right? You don't know the posterior, so that's always something that puzzles me. But I will leave this as an exercise to the reader to see that, yes, yeah, I'm gonna do that, to see that this is nothing else than the Bayes rule, because we're taking expectations with respect to the variational family, like the Q phi, and within these expectations, then this denominator actually is not that important. So that's what I'm going to say about it. And again, it's left as exercise to the reader. But given the reference below, I think it's quite plausible to know why this is reasonable. But if we don't trust me, that you should never do anyway, you need to, I can pitch you this as like, this actually makes kind of sense, because we can intuitively decompose the ELBO curve or the ELBO function in these two pieces. So the first one is trying to fit the data, because you have like the likelihood function. So you have some data, you want to explain this well. And the second is kind of the distance, or between your prior and your variational approximation. So it's a balance again between the data. You want to fit the data, but also you have the prior, and this is kind of in essence trying to do the balance, right? But anyway, let's take this for granted. And again, Chris does a much better job explaining this, so watch his video. And let's just give some kind of concrete example to this. So I'm going to do something very simple, which is I'm gonna try to do parameter recovery of a sample data set. So what I did was to take a gamma distribution, which we don't care about how it looks, but the gamma distribution might depend on one parameter alpha, and because I own the simulation, I know alpha is 2, and I just created a bunch of samples of this distribution, and this is kind of this density that you see. And the question is like, how do I recover alpha using this method and the tools that I have available in the JAX ecosystem? So I'm going to go kind of bit by bit in this toy model example. And again, I'm going to share the code. So please just take this as a gist of like it should work in a reasonably coherent way given the math. So the first thing we start with is with the Bayesian model, which again, this has nothing to do with any approximation, but you as a modeler try to model the data generation process. So in this case, the model is a function which receives some input, which is going to be the observed data. And then you know that for the gamma distribution, it depends on one parameter that is called the concentration. And let's say we know that it must be positive. So in this case, we take a half normal distribution, which is like a positive prior. Again, I don't want to talk much about the prior selection, but it's quite reasonable for the problem that we have in hand. And this is what we would like to learn. And how are we going to learn this? Well, we are going to, we know, or let's say, or like we're giving the fact that we're sampling from a gamma distribution and our observer variable is set. And rate is another parameter for the gamma distribution, but we're going to set that to 1 because we want to do like univariate variable. So you can sample from the model and get some kind of data points coming from this prior, but of course we want to learn this from the data. So how do we do this? So there's an easy way and a hard way, and I'm going to tell you the hard way just because one has to do it once in a lifetime. And it's, okay, let's actually write the approximation by hand. So I'm going to approximate the concentration parameter with a normal distribution, right? So this is what in NumPyro you call like a guide. And then if I want to approximate this as a normal distribution, I have 2 parameters to learn. So this is what I want to learn, which is the mean or location and the standard deviation or like the scale, right? So these are 2 parameters that I want to learn, and that's why I mark them as params in NumPyro. That's it. But then you could be wondering like, wait a second, but the concentration is positive. How you can approximate this with a normal likelihood? Or with a normal distribution. Normal distributions can take negative values. So that's fair. So what we do is actually take this base distribution coming from this normal approximation and then transform it with an exponential function. So this just take the normal approximation, but actually through approximation, you need to take some transform that make this positive, for example, taking the exponential. And then they're good because the concentration is positive. And then the guy just needs to map the parameters in the model to the parameters in the approximation. So this is really doing it by hand. And then what's the workflow in NumPyro? Well, there's a very nice ELBO loss, which is already something that you could import. The parameters are not important now. Then you have an optimizer. So if you're coming from deep learning, add-on optimizer seems like a pretty reasonable choice. And then you baked into this handy SVI object where you have the model, which is kind of the data generation process, the guide, which is the variational approximation, the optimizer, and the loss. And then you just run it. So about JAX, you will see that I'm having these like keys, which are kind of random generators that I need to carry with me just because JAX is works in a functional paradigm, so we don't have like a global random state, but that's not really important, but I still want to put it there so that you can reproduce this. And that's it. So we run the optimization. It takes like a few milliseconds, and on the right or left-hand side, depending on where you are, you see kind of the ELBO loss going down as you optimize, which is what you typically want to get. And then on here, on the upper part, we see the posterior distribution, the approximation for the concentration parameter, which is around 2, which makes sense. And then we randomly generate samples from the posterior predictive, and it matches our data quite well. So this is the workflow. Define your model, define your guide, and just run the machine. How hard can it be? Well, in many applications, that workflow can get you to 80% of where you are. But if you really want to push it and you really care about kind of robustness of it, then I'm going to show you some tricks that you can do to actually build on top of this workflow. So for that, I'm going to use another relatively known data set, which is this 2-moon data set, which is a classification problem where you have like 2 classes, and we want to learn this nonlinear decision boundary. So the model is very simple because I don't know the decision boundary. I know it's not linear, so I'm going to throw a neural network because why not, right? But it kind of is not because we need it, but it's just to see how this can integrate to kind of deep learning libraries like Flax. So what we're going to do is like we're going to model our data as a Bernoulli likelihood. We have classes like 1 and 0, and the p parameter like of the probability of being 1 or 0, we're going to model with a very simple neural network, and that's how it looks. And again, this is just kind of the baseline, but you can do as much things as you can do thinking about Bayesian modeling. So I'm just want to show you how to like a neural network would look in Flax, which is very similar to how it would look in PyTorch. So you can just define a class where you define, we're going to use Flax, a new API, and JAX to just carry these random generators. You need to specify the number of hidden layers, and this is what you do in the initialization parameter, and then on the call method, you do the forward pass. So we have a lot of layers here. We're going to use tanh kind of functions between the layers, and at the very end, we're going to use sigmoid as an end activation function. And we're going to take 4 and 3 layers, so very simple, but here you can use any type of neural network that you want. All right, so the NumPyro model, it's the data generation process. How do I kind of specify my Bayesian model? So again, here, there's a very helpful random NNX module function, which just lets you wrap any type of neural network, and you can just plug this into a NumPyro model, which is very handy. So you receive the X and the Y, which is the features and the target, and then you can specify priors on any of the components. So is it useful for this case? Probably not, but I just wanted to show that you could, for example, say, okay, for the bias, I'm going to use a normal distribution, and for the weights, like a soft Laplace, because like, why not? It's not gonna make a big difference now, but I just want to show you that you can really go into specifics about the specific priors of your neural network. Then we just take our neural network, and it's which is wrapped in this random NNX module, so that NumPyro can understand this kind of variable. And then, we just save our P as a deterministic variable, which is nothing else. I want to track this variable, and I'm going to sample from a Bernoulli distribution coming from this variable P, right? So it's exactly what I described in the diagram before. So it's a very simple model. So as a good Bayesian, I should always do prior predictive checks. And here on one hand side, I'm looking into the latent variable P, which is oscillating around 0.5, so not very informative. And for the kind of, let's say, high density interval of this prior predictive check for P is also quite wide. So I'm not putting any useful information in the priors. And now I'll do the optimization again. You need to define the guide, and the NumPyro gives us a very nice feature, which is you can actually tell NumPyro, hey, just write the normal approximation. I don't want to deal with all those transformations. Just handle that for me. And that's a trade-off that you need to understand. But to get started, it's very handy. You get the optimizer. And I want to emphasize on the learning rate. So this is something that you need to set. And again, you baked into the machine, model, guide, optimizer, loss, how much you're going to run, and just run the machine. You get this nice ELBO curve. Kind of that's it, right? But then I wanted to do something interesting. So I decided to make my life very complicated and to extend this into things that could actually be useful in practice. So I decided that I wanted to write the autoguide myself for this neural network in a way that it was kind of generalizable, so to say. It was a pain. So this is where I spent 90% of this presentation trying to do it. I almost failed, but I pulled this off. And the learnings were like, for this problem, it wasn't worth it. It didn't change any kind of performance, and I'm going to give you some tips on how the trade-off between, there's actually middle grounds between having a full auto guide and something custom. Because here, for example, how you initialize the parameters of the neural network matters. So I did the stupid mistake, initializing the parameters at 0, and that's what's bad, of course. Then the variance of the initial gates also matters quite a lot. So, and you need to pay attention to scales. So, so this was actually quite interesting, painful experience, and you can actually run it and see all of the tricks. I have a lot of comments. It was a pain. The other thing that you can do is have a custom optimizer, and this is something that really pays off because you can use Atom Optimizer, that's fine, but you can take all of the machinery from Optax to actually do it in a better way. So what you can do, for example, is to have a scheduler on which the learning rate actually decreases over time, so to say, so that you don't get kind of stuck, because I was very naively in some real project trying to tweak it by hand, and then I kind of had to grow up and discover this. And it's not really clear in the documentation, so I want to expose this. So this is very good trick. And recently it was added the fact that we could also add like a plateau contribution, which means that you can have the Atom optimizer, but still the optimizer can see the ELBO curve, and if it's getting into some plateau, then the learning rate also will decrease. So that actually can decrease your training time by 3 or 4 times. So this is really, really good if you want to do this in practice. The other thing that I wanted to do, and this is something that I think it would be a nice outcome of this talk, is to show you how to do early stopping. Because this magic of doing like SVI fit predict can take you kind of 80%, but in applications, we really want to control for overfitting because we're not really balancing here. And this is just a gist on how you do it. So actually you can take full control of the kind of optimization step. So you have like the step where you update your parameters with this body function, and then you run the for loop by hand, where you just iterate over the states. And here we can use this JIT just-in-time compiler to make this really, really fast. And then once you have this state, you can compute losses on the training set and the validation set, but you can compute anything you want, and then you can specify the early stopping condition as you want. So for example, I did this everything by hand. There's probably a better way, but here, for example, I add this patience counter where I told the model, hey, I just want to make sure that if the validation loss is bigger than the training loss in 10 times, then you should stop. And this is how actually it looks after I trained the model at 37%, the patient's criteria was fulfilled, and actually save some time and compute into doing early stopping. And I guess it's hackable, but it requires some efforts, but I think in real application, it's interesting to know that this is possible. And then you can do the model evaluation. So for example, here I'm gonna use the A over area under the curve, and instead of having a value, here I have a posterior, which is kind of interesting. And yeah, I'm not really overfitting. They look pretty reasonable, and these are the predictions. Let's say this is like the posterior predictive mean, and I see kind of, okay, I've learned the nonlinear boundary, so quite reasonable. And here, like something that is valuable about these models is that I don't only care about the point prediction, but also the uncertainty. So here we're plotting also the uncertainty of the p parameter, let's say the width of this high density interval, and you see that close to the decision boundary is actually pretty big, but as you get out of it, the model gets more confident. And we believe that this is very useful information as well, besides the point prediction. Yeah, this exercise of doing some extrapolations to see how this would work. So as we see, kind of the neural network just learned this kind of nonlinear part on, let's say, around the training set, and let's say outside the training set, it just goes linear. And one thing that it's kind of nice in this case is that even though the kind of outside the training set, these things are linear, still the uncertainty is actually growing. So the model is less confident about where the decision boundary lies. And also I did this to explicitly show how to do this train test split. So some tips and tricks. So actually this was very hard to write as well because I don't have a definitive answer. So when you have large data sets or when you want to do like really fast iteration loops, like SVI is a really good place to start, even though at the very end you will do like MCMC. So because one of the most valuable things that we have is our time. So you can speed up this development cycle is quite good. If you need this to be relatively fast in production systems, then that's helpful. And if you can live without having an exact posterior, but maybe you can do some post-processing afterwards or so on, you can do it. When to use MCMC, like if you have small to medium data set, that's also changing with the capability for running these models on GPU. When you need precise posterior samples, so if you want to do like inference, and you really care about this, then, for example, in a media mix model where we have a lot of parameters, even though that it might take long, I think it's worth it because you do care about this uncertainty quite a lot. And the uncertainty estimate of SVI, in general, I've seen that they're typically underestimating the uncertainty. And something that is not written here, but also the geometry, like if you expect these posterior distributions, or like if you see that could be multimodal, but your approximation is just unimodal with a normal distribution, then it's not going to work. Yeah, MCMC, if you have time for long computation, so if you need to run like a big model maybe once a week, and it can just run for 24 hours, but you get really good estimates, that's great. So tips and tricks is like, if you use NumPyro and JAX, go for GPUs if possible, because they can just go really, really fast. I'm talking about 50,000 time series, state space model, hierarchies, features in like 7 minutes. Really go into trying to do like mini batching and all of these things from deep learning, especially the schedulers and the optimizations. So you can go and do much better than just pure Atom. And also, JAX is not always faster than NumPy. And this is also something that I learned by heart. So doing things with JAX and expecting like speed up is not a good idea. And sometimes, like many times, NumPy can be very good on GPU. So for example, something that we did was to do the posterior predictive steps on the CPU. So there's some subtleties when thinking that JAX is always better. No, it's not. So think about the use case. And of course, there are other Bayesian methods to do kind of inference. So for example, in the NumPyro documentation are other variants of MCMC. And actually, you can integrate samplers from BlackJAX and FlowJAX into NumPyro models. That being said, you can actually integrate all of these methods with PyMC models through a package called Bayux. So the ecosystem is actually trying to separate kind of the API, the front end to the computation engine. So it's very exciting times. And so I have some reference that I'll share with you, which it's not exhaustive, so to say, but it's kind of very practical. So yeah, like Pyro has a lot of good information and tips and tricks about it. There are some really nice papers and of course, stand documentation. And again, go and check Chris' talk, which is really, really good. Yeah, that's it. Thank you very much.
So we have questions online. So the first one, do you want to read it out?
Yeah, if you experience how variational inference and expectation propagation compare, what strengths and weaknesses and practical concerns? I don't know. I haven't really worked with expectation propagation. SVI has worked for my applications pretty well, and MCMC, of course. The second question.
We have a bit longer question, but
okay.
I think it's...
With variational inference, you're trading difficulty of sampling the posterior with running stochastic gradient descent or optimization. SGD might require very small learning rate and large number of steps to converge when gradients are noisy. How do you ensure that the optimization actually converge in production and for large real-world problems? So I would say this is kind of the same as how you do like a deep learning model, right? You still need to understand this. There are various techniques to make sure that this work properly. I guess in this Bayesian setting, you could do a kind of something that I wasn't able to pull the PR, but you can do like prior and posterior simulations to see that these are coherent, sensitivity analysis. So I'm not saying that SVI, you can just throw it in and it's going to work. As always, you need to fine tune it yourself depending on the model.
Are there any other questions? If not, please let's thank the speaker again. Juan, thanks for the amazing